Mechanisms for representing small numbers. Based on the set size signature found across various species in tasks assessing small number discrimination, many researchers have proposed that there are at least two distinct mechanisms for processing number: a precise small number system and the approximate number system. One proposed mechanism that likely underlies small number discrimination in some situations is an object tracking system. This system was described originally by researchers examining human visual attention in order to explain the ability to track objects in the world. The mechanism entails a small number of mental indexes that point to individual objects and enable people to keep track of them as they move in and out of view. Across many different types of tasks, e.g., tracking the movement of 4 specific objects among many other moving objects, adult humans appear to be limited to tracking about 4 objects on average. Thus, the set size limit seen in the aforementioned studies of small number discrimination fits the general model of the object tracking system. Importantly, though, the object tracking system is not meant to be a model of a number system per se. Instead, the output of a system such as this might be to track, for example, that object exists in one container, while object exists in another container, rather than outputting an analog magnitude for the numerical value of the two sets. Yet, the output of the object tracking system still provides a basis for comparison between numerosities. Additional evidence for the existence of a separate system that may be utilized when representing small sets comes from studies in which human infants and animals must discriminate between two sets of objects in which one set is small and the other large, e.g. 2 versus 8. Human infants, as well as a species of fish, guppies, can discriminate sets in which both numbers are small or both numbers are large, but have difficulty when one number is small and the other is large. It is thus possible that there are two systems governing discrimination in these cases, and further, the output of one system cannot be compared to the output of the other. Specifically, analog magnitude representations will provide information about the total value of the set, but object tracking representations will not. In contrast, some researchers have proposed that both small number and large number discrimination can be processed by a single system of analog number representation. The system, though, will be primarily effective in situations in which the ratio difference is large, and for smaller ratios, the output of an object tracking system will dominate. In sum, though it is clear that many species can process and discriminate both small and large quantities, researchers are still actively examining the role of these two potential cognitive systems. Outstanding questions remain regarding what situations might elicit different systems, the development of these systems in humans and other species, and their evolution. Operations. In their seminal work on numerical cognition, Gallistel and Gelman have detailed many aspects of nonverbal number representation, including the features that indicate a true concept of number. The ability to perform operations, or procedures on numbers, is a proposed hallmark of this concept. For example, a true concept of number should include an understanding that number is an ordered system. That is, not only are 4 and 8 different quantities, but also 8 is larger than 4. Evidence for operations in animal species and humans has been growing over the past 2 decades, with special focus placed on addition and subtraction, as well as an understanding of ordinality. More broadly, operations could also underlie foraging behavior, particularly when foraging decisions are based on sensitivity to the rate at which a site provides food, which will be discussed in Chapter 7. Addition and subtraction. It is reasonable to think that addition and subtraction are operations that are specific to symbolic representations of number, like Arabic numerals. From early in schooling, humans are taught to write out numbers, inserting plus and minus signs to denote adding and subtracting. Yet, it is also not a stretch to recognize that the nonverbal numeric representations discussed thus far in this chapter can also serve as the operands for these procedures. A study by Wynn, 1992, with human infants provided a nonverbal experimental procedure with which to examine spontaneous addition and subtraction of small quantities. 5-month-old infants were shown one doll being placed onto a stage, and an occluding screen was placed in front of the doll. A second doll was then placed on the stage, also behind the screen. If infants can represent the first doll after it was occluded, and then add the second doll to this representation, they should respond with longer looking if the screen is dropped to reveal only one doll, 1 plus 1 equals 1, than if it drops to reveal two dolls, 1 plus 1 equals 2. Infants did look longer at the impossible outcome in the addition event, and they also looked longer at an impossible subtraction event, 2 minus 1 equals 2, than a possible event, 2 minus 1 equals 1. An additional experiment found that infants looked longer at events depicting 1 plus 1 equals 3 than 1 plus 1 equals 2, suggesting that the representation of objects behind the screen was more precise than simply 1 plus 1 equals more than 1. In Wynn's original study, however, other magnitudes such as surface area were not controlled. Because all of the dolls were the same size, it is possible that infants were not responding to number per se, but to an impossible amount of doll stuff. Subsequent studies controlled for other variables by either using alternative objects or by showing that addition can occur across modalities. For the latter study, 5-month-old infants first learned to associate the arrival of animated dolls with tones. In test trials, one doll was moved behind a screen, and then a single tone or multiple tones occurred, indicating the arrival of additional unseen dolls behind the screen. Infants looked longer to events in which an impossible outcome occurred, e.g., 1 doll plus 2 tones equals 2 dolls, or 1 doll plus 1 tone equals 3 dolls, than events in which a possible outcome occurred, e.g., 1 doll plus 1 tone equals 2 dolls, or 1 doll plus 2 tones equals 3 dolls. In many ways, the addition abilities seen in these studies fit the findings from the choice tasks detailed in section 6.4.1. In the choice tasks, which occurred years after the looking time studies, observers saw objects added one by one into an opaque container, and approach responses appear to be based on representing all of the objects. Animals have also shown the ability to add and subtract in studies in which looking time to possible and impossible events was measured. Rhesus macaws look longer when impossible addition and subtraction outcomes are revealed, both when the quantities are small, 1 plus 1 equals 3, and large, 4 plus 4 equals 4. 4 lemur species were also found to look longer at impossible outcomes of 1 plus 1 events, depicted with lemons, even when surface area was controlled. The ability to represent simple addition and subtraction operations has also been seen in bird species. In these studies, looking time is not used as the dependent measure, and instead, behavior such as pecking keys or searching newly hatched chicks is examined. Thus, there is evidence across a variety of experimental paradigms that, similar to the ability to discriminate quantities, the representation of arithmetic operations is found beyond the primate order. See also box 6.3. As will be seen below, though, the underlying cognitive mechanisms for these operations remain under consideration. Box 6.3. Training animals to use number symbols. In the study of numerical cognition, some research programs have focused on the ability of animals to learn associations between number words or symbols, e.g., Arabic numerals, with quantities. For example, Alex, an African gray parrot, was trained to vocalize English number words and associate these words with Arabic numerals as part of a larger training process that included learning to respond to various spoken questions. When Alex was shown two numerals, e.g. 2 and 4, of the same size, and asked which bigger, he was able to respond vocally with 4. To do so, Alex likely was linking the vocalizations to the visual symbols and the corresponding numerosities. Boyson and colleagues taught chimpanzees to use Arabic numerals through a process that began with initial training of one-to-one correspondence between food pieces and non-edible small objects, e.g. 2 food pieces on a plate would be matched to a plate that contained 2 small cloth balls. Over time, the object plates were replaced with Arabic numerals, and ultimately the chimpanzees could touch a corresponding numeral for arrays of 0 to 8 objects. This research program also provided one of the first examinations of arithmetic in an animal species, Figure 6.11, when one of the chimpanzees, Sheba, was allowed to search a room for hidden food items or numerals in various locations. She was able to return to the starting location and report, by touching a numeral, the summed amount. The ability to sum, symbolic representations of quantity, has subsequently been found in other studies with chimpanzees and with Alex the parrot. Additionally, Oshoff et al. 1997 found that squirrel monkeys that had been trained with Arabic numerals could compare pairs of numerals so as to pick the pair that summed to the greater amount. Figure 6.11, testing room for examining a chimpanzee's ability to add. The circles depict food items, although on some trials the food was replaced by Arabic numeral placards. The process of training associations between numerals and quantities is time-consuming, and it has been proposed that these studies do not reveal much about numerical cognition beyond that of studies examining spontaneous numerical discrimination and operations. One particularly seminal finding, however, has been the role of numeral use in a reversed contingency task. Boyson and Berntsen, 1995, created a task in which numeral-trained chimpanzees had to choose the smaller of 2 amounts of candies to receive a larger amount. In this situation, though, the chimpanzees seemingly could not inhibit choosing the larger amount of candy, even though that choice led to a smaller reward. In contrast, when the Arabic numerals were used in place of the candy arrays, chimpanzees readily chose the smaller number and subsequently gained the larger amount. Thus, the numerals seemed to represent magnitude symbolically and aid the inhibition of prepotent responses to actual food quantities. This work has proven informative to the study of inhibitory control in young children. Cognitive mechanisms of addition and subtraction. In its traditional definition, addition involves combining 2 or more number representations to form a new representation, the sum. The approximate number system would thus account for addition because an analog magnitude representation could be combined with another analog magnitude in such a way as to yield a total or sum. It gets trickier when one considers the object tracking system, however, because as discussed above, that system does not create a representation of a set, only the set's individual components are represented. For example, in an addition task with small numbers, one object is tracked as it goes behind a screen, and then another object is tracked as it too goes behind a screen. Under object tracking models, the representation is then object-object, which could be compared to the impossible outcome of object that is seen when the screen drops on test trials. Thus, in addition and subtraction tasks using small quantities, it is possible that observers are not creating a magnitude sum after all, but instead are relying on the object tracking system. This system, however, cannot account for tasks in which operations are performed on large quantities due to the set size limit. One such study has already been mentioned, i.e. 4+4 events, and others include studies with human infants, 5+5 and 10-5 events, and chimpanzees, 6+10 events. In these studies, it is proposed that magnitudes and sums are being represented by the approximate number system. Ordinality. At a basic level, a number can simply serve to differentiate items and be used as a label, like Wayne Gretzky's jersey number 99. This type of representation of number is on a nominal scale, and it does not allow for inferences to be made about relative magnitudes, e.g. 99 is greater than 50, though basic equality and inequality determinations can be made, e.g. 99 does not equal 50. In contrast, when numbers are represented on the ordinal scale, they are ordered in a rank based on their relative magnitudes. Tests of relative numerosity, like those described in section 6.3.2 and the addition and subtraction studies described above, suggest that animals do represent number on an ordinal scale, but it is important to note that behavior on some tasks can be interpreted as the result of representation on a nominal scale. If an animal is trained to choose the larger of two numerosities, for example, it is possible that what is ultimately learned is a set of pairwise contingencies, e.g., pick 7 when paired with 6, but pick 6 when paired with 5, etc., instead of an ordinal rule, e.g., pick the greater magnitude. A more direct test of knowledge of numerical order would entail testing animals on a range of numbers outside of the range they were trained in. Brannon and Terrace, 1998, presented rhesus macaws with a touch-sensitive screen that displayed the arrays of size 1 to 4 simultaneously. The elements of the arrays differed in size and shape, and they appeared in various locations from trial to trial, figure 6.12. After the monkeys learned to touch the arrays in increasing order, new test trials were inserted that contained arrays of size 5 to 9, but only 2 arrays were presented at a time. Even with these novel pairs, e.g. 7 and 9, the monkeys responded correctly by touching them in increasing order, though as predicted, response times and accuracy followed Weber's law. Figure 6.12. Examples of displays used to train and test rhesus macaws on numerical order in Brannon and Terrace 2000. The elements of the arrays varied in size, shape, and location from trial to trial. Okay, so it's like a grid, and in each square of the grid you're seeing shapes of different sizes, and there's a different number of shapes. Wow. So even in one trial they show like some are lines, some are rectangles, some are ovals, and they're discriminating between all that. That's really impressive. A question remains as to whether the monkeys learned the concept of ordinality from the training trials, or if they already had this concept prior to the study. A clue comes from one monkey that was unsuccessfully trained to respond to arrays of 1 to 4 in an arbitrary order that was not based on increasing or decreasing magnitude. The fact that this monkey did not learn the order, but later was able to learn an increasing order, suggests that monkeys may spontaneously order magnitudes. The arbitrary order would thus have been in conflict with this existent representation and formed a more difficult order to learn. In sum, a wide range of animal species can not only discriminate between numerosities, but can also add, subtract, and order. Though the cognitive and neural mechanisms supporting a concept of number are still under investigation, the comparative study of numerical processing, as well as timing, has led to great advances in our knowledge. These findings may ultimately influence mathematics education, as well as the understanding of certain neurological disorders. This chapter will end, however, by presenting in Box 6.4 an ongoing question for research into numerical cognition, one that is specific to human cognition, but in turn helps to complete the comparative framework. If the cognitive systems for number that humans share with other animals form the foundation for our human unique mathematics, what may be the intervening role of language, particularly the role of words for precise quantities like 8 or 10?